In this lesson, we're going to be taking a look at exponential functions. These exponential functions enable us to predict the future and rediscover the past. So our objectives are going to be to evaluate exponential functions, graph exponential functions, transform graphs of exponential functions, and we're going to use compound interest formulas to determine interest. Okay. Exponential functions. They're functions whose equations contain a base b and a variable in the exponent. They also describe many real-world situations, such as these listed here. All right, let's look at the structure of an exponential function. We write an exponential as f of x equals b, some value, some number, raised to the x power, or instead of f of x, we can use the notation y equals b to the x. Where b is greater than 0, b cannot be 1. If b is 1, then you're taking 1, raising it to any power, which means your answer is just going to be 1. So there's no change there. Okay, so in your exponent could be any real number. These are two examples of exponential functions. 2 raised to the x power, where the base is 2, and the variable is the exponent. And because the base is greater than 1 and x is positive, this is what we call an exponential growth function. If you look down here, you'll see 2 graphs down here towards the bottom. Okay, this is actually y equals 2 to the x graphed. We'll take a look at that more in detail in a minute, but this is what we call a growth function because as x increases, the y values of the points on the graph get higher and higher. Going back up here to another example. Okay, look at this base. It's a value between 0 and 1. X is also positive here, so this is what we call a decay, an exponential decay function. And here's a graph of that decay function. You can see as you go from left to right on the graph that the y values of these points are decreasing and getting smaller. Again, we'll look at that in more detail in a minute. One of the objectives that I mentioned is that we're going to evaluate exponential functions. So we're going to approximate the number, the answer, using a calculator. And we're going to round to 3 decimals if necessary. So just reminding that we're going to be using a scientific calculator. So there might be a little learning curve in finding where some of the keystrokes are. But since we're not meeting face-to-face, you might want to go to YouTube and type in your calculator model and then ask it how to find certain keystrokes that we're going to be needing. Okay. All right, so here, let me get situated. Okay, I'm going to kind of draw this squiggle line because these 2 problems that fall above the squiggle line, or above the squiggle line, these 2 problems right here that we're answering come from this function right here. So given that f of x is 2 raised to the x, find f of 4. Well, simply, we're just going to plug in 4 for the exponent here, and then we're going to go to our calculator, find an answer, round to 3 decimals if necessary. So f of 4 equals, so if I put 4 in for x here and 4 in for x here, I would record 2 raised to the 4th power. So f of 4 is equal to, you could go to your calculator, or if you know what that is, which is 16, you can just record it. Okay, the problem to the right here, we're still going to use the same function over here. So everywhere you see x, replace it with 5.6, so that looks like 2 raised to the 5.6 power. A calculator is going to be necessary to find that answer. It's 48.503. Just kind of off to the side here, the keystroke you're looking for to find this answer of 48.503, on your scientific calculator, you might want to be looking for this little caret key, it's called, raised to. You would just type in 2, the caret key, and 5.6, and then the equal. It should result in this answer. If your calculator doesn't have that little caret key, you might find the key on your calculator that looks something like y raised to the x, or it might even be x raised to the y. This suggests an exponential situation. If you have either one of these buttons right here, you would then type in 2, then hit this key, and then hit 5.6. Okay, again, if you're struggling with getting these answers right here, then you might want to go to YouTube and kind of look that up. These 2 problems right here that fall below the squiggle line don't have anything to do with this function. They're just on their own. This is just making certain that you know how to use the proper keys on your calculator to get the answer. So 5 raised to the square root of 3. So you're gonna have to look for your square root key, and then just kind of, play around with it until you get this answer, 16.242. Okay, this right here, just be real careful when you're entering this into the calculator. I might enter parentheses 2 divided by 5, close parentheses, and then raise it to the third power. If done correctly, the answer that results is this right here. Another way to find this, if need be, is that when you have a fraction taken to a power, I can apply that power to both the numerator and denominator, meaning, okay, I could actually go through and find 2 cubed, which is 8, and then cube the 5. 5 times 5 times 5 is 125. So if I didn't want a decimal answer, this is the equivalent fraction answer. If you want to verify that this is correct, you could just go to your calculator and do 8 divided by 125, and the result would give you this decimal right here. So the purpose of evaluating exponential functions at this point is just to make certain that you know how to use the proper keystroke to get the answers. All right, we're going to return to just looking at some graphs of exponential functions. So we've got 2 of them down here. We've got y equals 2 to the x, a growth function, and we have a decay function from y equals a half x. Okay, I'm going to go ahead and include some arrows on here. Okay, when we look at this graph right here, what's happening is this graph right here is getting closer and closer to the negative x-axis. It doesn't just stop, but we've just kind of run out of some space here. But it might be good just to kind of extend a little bit and put an arrow on the end of that graph. So where did these points come from? Well, these points came from our creating a t-chart. We have it here. Okay, and some of the common numbers that we've used in the past under our x column as our input values were these 5 x values. So if I want to generate this graph that's already been graphed for me, this graph came from our taking turns plugging in each of these x values for the x right here, and then computing those values, and then going and returning to the coordinate plane and graphing them. So one at a time, I'm going to replace these x values in for this x. So the base is 2, the new exponent is -2. You can go to your calculator and compute 2 raised to the -2. Okay, not that you have to do this, but to remind you of some math that we've seen with regard to negative exponents. If I wanted to make that exponent positive, I would take this base of 2 to the denominator with this exponent, but adjusting that negative exponent to a positive value. And we put a 1 on top. We know this is 1/4, and 1/4 changes to the decimal 0.25. Certainly you could jump from the calculator to this decimal value right here. You should get 0.25. 2 to the -1. Again, I have a negative exponent. Okay, if I wanted to make this have a positive exponent, I would drop the 2 to the denominator, giving it a positive 1 exponent. And that's just 1/2. For the purposes of graphing, I'm going to change that to a decimal, and that's 0.5. Again, you could just go right to your calculator, 2 raised to the -1, the result would be 0.5. The base of 2 is now raised to the 0 power. Any base raised to the 0 power is always 1. Okay, now we're going to come over here to the grid and we're going to plot these points, -2 and 1/4. We'll go to where x is -2, jump up to 0.25, plot a point. Okay, right here, it's worth discussing. If you were at x equals -3, which isn't in my table up here, I would have a smaller answer than 0.25, so that's why the graph of this exponential function is getting closer and closer to the negative x-axis. Okay, returning to the table, plotting -1.5, that results in this ordered pair. 0, 1, that's our y-intercept. Plot the point 1, 2, x is 1, y is 2, so that would be about right here. And then the last ordered pair, 2, 4. So these should be enough points for us to understand the behavior of this graph and connect it. So kind of a couple things to observe here is that it appears that I have a horizontal asymptote at y equals 0. So y equals 0 is the x-axis. That serves as a horizontal asymptote on this side of the graph. But as you move to the right, you can see the graph is pulling away from the x-axis, and the graph is the y values are increasing without bound. That's why we call it a growth function. Okay, let's take a look at the exponential decay. Same situation. Let's plot some points to create this graph. Yes, this graph has already been created for us, but let's really dig in and see where this graph came from by looking at numerical values. Same x's. Now take turns evaluating this function for each of these different x's. So I've got 1/2 raised to the -2 power. Of course, you can go right to your calculator, compute this. Just be careful with the keystrokes, making certain you do an open parenthesis, 1 divided by 2, close your parenthesis, then raise it to the -2. At this point, mathematically, something that we can do, though, is this. If I want to make this exponent positive, notice this is a fraction in here, unlike what we had over here. 2 was not a fraction. Mathematically, what we could do if we wanted to make this exponent positive is I could take the base, okay, and I could reciprocate it. Make 1/2 become 2/1. If you perform that action, then you could come over here and adjust this exponent to positive. Well, this is just 2. 2 raised to the 2nd power is just 4. Same thing here. I have a negative exponent on a fraction, so let's reciprocate the fraction and adjust the exponent to a +1. This is just 2 raised to the 1st power, so that's just going to result in 2. I have a base raised to the 0 power. Any number raised to the 0 power is 1. A 1/2 to the 1st, that exponent is not necessary. My answer is just a 1/2, but for the purposes of graphing, we're going to change that to 0.5. Okay, again, you can go right to the calculator. The result will be 0.25, but just to remember some math here, if I have a fraction to a power, I can take the numerator to the power and the denominator to the same power. So 1 squared is just 1, and 2 squared is just going to be 4. And the result will be what we thought, which is 0.25. Okay, notice that these y values right here, as the x values are getting larger from -2 to 2, these y values are decreasing. That suggests that we have a decay situation as illustrated in this graph right here. Okay. Again, just talking about, do we have a horizontal asymptote? Yes, we do. It happens to be the x-axis, whose equation is y equals 0. But the horizontal asymptote only serves that purpose over here on this part of the graph. Okay, this graph up here is just increasing without bound, or if you move from left to right, the y values are getting smaller. So we do have an asymptote, but it really only has an effect of being the asymptote for this part of the graph right here. All right, so we've got an example of a growth and a decay function. We can see it visually that we have growth, and we can see it visually that we have decay here. We can also look at the numbers, the y values that we have here, and see how they're increasing. So that corresponds to the growth. We can see how the y values are decreasing, so that corresponds to the decay. Some other things, characteristics that we want to kind of be aware of for exponential functions are, yes, for exponential functions, we do have asymptotes, horizontal asymptotes. Both these graphs have a y-intercept of 1, and that's because when x is 0 as an exponent, anything to the 0 results in 1. It's good to talk about the domain of exponential functions. So the domain for both of these graphs are all real numbers, and the range for both of these graphs are 0 to infinity. Okay. On a growth function, we can talk about having an increasing interval. Well, this exponential function right here increases across its whole domain. It never decreases, so we would never talk about a decreasing interval other than to say if we're talking about this graph, that there is none. There's not a decreasing interval when this graph is entirely increasing. Okay, likewise over here, the graph of a decay function is going to be decreasing, so we have no increasing interval, and this graph is going to decrease across its whole domain. Okay, what's being mentioned down here is larger value of b on a growth function means a steeper increase. So what does the graph of this exponential function look like in comparison to the graph of this exponential function? Well, I went ahead and put into my graphing calculator a few exponential functions, as you can see here. Okay, hopefully you can. Okay, in y1 I have 2 to the x. In y2, I have 4 to the x. And then in y3, I have 10 to the x. So you can notice that the bases are increasing. 2, 4, 10. So let's kind of look at all these all together to kind of get an idea of what's happening with each of these graphs. There's our 2 to the x. I put a tracer ball on the next two so we can kind of see and observe their behavior. Notice that 4 to the x does also intersect at the same y-intercept 0, 1, but the graph is steeper. This is 10 to the x, and it's even yet more steep than the previous two. So this kind of suggests that as the b value increases, the graph has a steeper increase. And hopefully that kind of makes sense numerically as well. If we were to think about graphing y equals 4 to the x, if we put 4 to the x here, okay, then all these bases would become 4, and then all the outputs, okay, or at least right here when x is greater than 0, okay, all these outputs right here, okay, would be much larger numbers if my base was 4. So if my base was 4, if I came over here, I'm still going to be passing through 0, 1. But if my base was 4 and I had a power of 1, then my output would be 4. So at x equals 1, I would now go up and plot this point at 4. If this base was 4 and I squared it, I get 16. So if I came over here to x equals 2 and my output was 16, you can see that I'm up quite a bit higher than this previous point right here, making the graph become a little more steep. Okay. All right, with regard to the decay function, okay, what happens when our base is still a number between 0 and 1? Well, we were graphing y equals 1/2 to the x, but what if we changed a half to a fourth being smaller? Okay, it says that we have a steeper fall. So perhaps 1/4 to the x might look something like this right here. I'm still going to pass through 0, 1, okay, but the graph is going to have a steeper fall than 1/2 to the x, just because of this smaller base right here. Okay. All right, let's go ahead and look at the next objective. So far we've looked at evaluating exponential functions and graphing exponential functions. Okay, so on the next page, what we're going to look at is transformations of exponential functions. We want to be able to move these exponential functions up, down, left, right, maybe do some reflections on them. So let's do a little recording over here of what we remember about transformations and what effect they have on graphs. Okay, if we study this equation right here, b again is the base, but notice that instead of having just x up here, we have a minus h value, and then maybe we're adding or subtracting something to this exponential. So let's come over here and define what we remember about h and k and the effect that it might have on a graph. So that's h. H is going to correspond to a horizontal shift. The k value is going to tell us the amount of the vertical shift. All right, we have 5 examples here, so let's see how we can respond to them. Okay, if our equation is y equals 2 to the x minus 3, okay, just kind of looking at what we have here, we have a base 2 function, because the base is 2. So the parent function is actually y equals 2 to the x. This is an exponential growth function. It's a growth because this base is greater than 1, and we have a positive exponent. We have a positive x here. There's not a negative in front of x. So what's the transformation based on what we remember? Well, this minus 3 is going to be our vertical shift, so this is going to tell us we're going to take our parent function and we're going to move it down 3. We might choose a couple of points that are on the parent function and then take those points and move them down 3 to produce this new graph right here. All right, we'll look at some graphing of it in just a minute, but let's just kind of identify the transformations based on the equations we're given. Example 2, okay, it's a base 1/4 function. It's an exponential decay because 1/4 is a number between 0 and 1, and the x value up here is positive. There's not a negative in front of it, so it is a decay. The parent is 1/4 to the x, so the transformation is just going to be wrapped up in this right here, this minus 3 that's with the x, not down here without the x. So you might remember that horizontal shifts are opposite of logic. So instead of going left 3, we're actually going to go right 3. So what happens is we might want to start by graphing the parent function and then choosing a few kind of key points on this parent function, and then choosing those key points, move them all right 3, and then produce a new graph. Example 3, base 5 function. It's an exponential growth because the base 5 is greater than 1 and there's not a negative in front of the x. We have two transformations here. Okay, this plus 4 is going to tell us that we're going to move the parent function, y equals 5 to the x. We're going to move it left 4 and up 1. Okay, example 4. This is a base 2 function, not negative 2 function. We think of that negative as being out front. So if you want to think about having some parentheses here, it might look like this. We still have a base 2 function. The parent is 2 to the x. Okay, it's called a decay, okay, right here, even though we have a positive base, we have a base bigger than 1 and a positive x, because this right here, this negative out front, has the effect of making this graph of 2 to the x reflect through the x-axis. So if we have a reflection through the x-axis, that's no longer going to be growth, it will be decay. We'll be graphing this one in a minute. So reflection through the x-axis. All right, let's look at 5. Okay, 5 is a base 2 function. Okay, you might think that it's going to be a growth because 2 is greater than 1. However, notice that in front of x, we have a negative. Okay, the parent is still y equals 2 to the x. This is another transformation where we have a reflection. This is actually going to be a reflection through the y-axis. So the takeaway from these two examples compared side by side is that if the negative is in front of the base, we have a reflection through the x-axis, but if the negative is with the x, then we have a reflection through the y-axis. Let's do a little bit of graphing. Okay, in this first example down here, it says for us to graph the parent function 2 to the x, and then once we get that on the grid, let's go ahead and produce this graph right here, which is just a transformation of this parent function. Okay, you might remember 2 to the x. You might want to remember that. You might remember that from what we just did on the other page. Some of the key points are when x is 0, y is 1. When x is 1, the output is 2. When x is 2, the output was 4. And for me, it's probably quite enough for me to go ahead and sketch the graph. So I know it's an exponential graph, so it's going to look something like this. Continue off the grid, put an arrow. Now, paying attention to how to produce the graph to the left of 0, 1, okay, notice that what we did was we came down below y equals 1, but we never fell below the x-axis. This serves as a horizontal asymptote at y equals 0. Okay, now we're going to go ahead and graph this new function right here. Okay, but we notice that we have a translation of down 3. So I might just take some key points right here. And move all these points down 3. Probably be a good idea to start with the horizontal asymptote though. The current horizontal asymptote is at y equals 0. Let's move that down 3 as well. So when you move the horizontal asymptote down 3 from y equals 0, okay, you're right here. So I'm going to go ahead and sketch in a dashed line to represent my horizontal asymptote for my new function. Now I'm going to go back and take these ordered pairs and move them down 3. So 1, 2, 3. This point's been shifted to here, which makes sense. When I produce the graph going off this way to the left, I know that this kind of lane right here, if you will, this vertical distance is just 1. So I have to drop below that ordered pair, but guiding myself out this way, I would not fall below y equals -3. I'm coming back and moving the other 2 points down 3, and then I'll connect them. Graph goes something up like that. So we can see a shift down 3 of our parent function, y equals 2 to the x, to produce our new function right here. Okay, let's respond to these questions right here based on my new graph. So what's the horizontal asymptote? Well, y equals -3. What's the domain? Okay, well, my domain's still going to be all real numbers. Okay, just by shifting my graph down 3 doesn't mean my domain's going to change. All right, and what's the range? Well, the range did change. Now my lowest y value is going to be at right above -3 up to infinity. So we're going to do a parenthesis. We don't want to include y equals -3 because it serves as an asymptote, a horizontal asymptote. So your range is -3 to infinity. Looking at these equations right here and graphing them. Okay, we're going to start with the parent function 2 to the x again. Okay, let's graph y equals -2 to the x. We saw that equation up here in example 4. We see that with y equals -2 to the x, that we have a reflection through the x-axis. So if you can identify the transformations, you won't have to do a t-chart. You can always do a t-chart if you want, but the quickest way to probably graph something like this is to observe the changes on the parent function based on what's going on in this equation. So let's draw a reflection of 2 to the x through the x-axis to get y equals -2 to the x. So here's the x-axis. Oops. If I draw a reflection, the x's will stay the same, but the y's will change. So if the x's stay the same, the y's are going to become opposites. This point right here is going to become 0, -1. So if I want to try and create a mirror image through the x-axis, which is my axis, my reflection, my axis of reflection, okay, then I'm going to have this graph come up closer to the negative x-axis this way from below it and go off the screen this way. This ordered pair 1, 2 now becomes 1, -2. And this ordered pair at 2, 4 becomes 2, -4. So same x's, opposite y's for a reflection through the x-axis. Okay, and then just trying to draw a mirror image of this graph through the x-axis, I would have something like this. Okay, we can talk about domain, range, and horizontal asymptote with regard to this as well. The domain didn't change. However, with that reflection, we do have a different range compared to the parent function. The range is now -infinity up to but not including 0. And we still have the same horizontal asymptote over here on this part of the graph at y equals 0. Okay, let's see what this graph looks like. Y equals 2 to the -x. Well, based on this equation up here, we said it's a reflection through the y-axis. So returning to looking at our parent function, let's think about what this graph would look like when it's reflected around the y or through the y-axis. Okay, so if we're reflecting through the y-axis, then our x's will become opposite, but our y's are the same. So this point at 0, 1 will just remain at 0, 1. This point right here at 1, 2 will become -1, +2. So these two are mirror points. This point right here is going to be reflected, when I'm reflected through the y-axis, its mirror point would be right here. So what happens is, to create a mirror image, I might draw something like this. Oops. And then come down. But now this side of y equals 0, over here, the positive x side, becomes our horizontal asymptote on this graph. Okay, we can talk about y equals 2 to the -x's domain, range, and horizontal asymptote. The domain didn't change. It's still all real numbers. Okay, the range didn't change from the parent function. It's 0, not including 0 to infinity, and it still has the same horizontal asymptote as well. All right, and that's going to be enough for this video. So in the next video, we'll start with what's down here, natural base E.